Imagine that for every particle we know, the ones making up us, planets, stars,
Mm-hmm.
there might be a hidden dark version.
Mm-hmm.
Like we have the photon, a particle of light, right?
Yeah.
Let's see. Could there be a dark photon working somewhere we just can't see?
That's exactly the idea, and it's a really captivating one we're diving into today.
Right.
This concept, the dark photon, it suggests a new kind of force carrier. Like our familiar photon carries electromagnetism.
Yeah.
But this one would come from a theorized dark sector, basically a whole set of particles that just don't interact with ordinary matter and forces, the ones we know from the standard model.
So a whole invisible set of particles, maybe even a whole new force. Wow. Okay, for this deep dive, we've been looking at some pretty serious research on this.
Oh, absolutely. Yeah, our whole discussion is based on a really thorough review paper.
Right.
It pulls together the theory behind dark photons and, crucially, all the different experiments trying to hunt them down.
And it makes a distinction, you said.
Yes, exactly. It clearly separates the possibilities into two main camps. Dark photons with no mass, like our regular photon,
Uh-huh.
and those that do have mass. And each type, well, they behave differently, and we have to look for them in different ways.
Okay, but why should this dark photon idea really grab our attention?
Yeah.
I mean, it sounds a bit out there.
Well, because it could be a really fundamental piece of the puzzle. If we understood dark photons, it might just unlock the secret of dark matter.
Ah, the big one.
The big one, that invisible stuff making up most of the universe's mass, shaping galaxies. And it could also point to totally new forces, stuff beyond the standard models, like peeling back another layer of reality.
A hidden layer of reality. I like that. So where do we start? What's the plan for exploring this?
Okay, so we'll start with the basics. What are dark photons? Especially, what's the difference between massless and massive ones?
Yeah.
We need to touch on something called kinetic mixing, too. It's this cool idea about how dark photons might subtly interact with our photons.
A subtle link.
Yeah, a potential loophole for detection. Then we'll look at the theories behind them, where they might fit into cosmology, maybe even as dark matter.
Mm-hmm.
And finally, we'll get into the really clever experiments scientists are using to try and find these things.
Sounds like quite a journey. Okay, let's kick off with the massless kind. What's the main thing about them?
The key thing, the defining feature, is that they don't directly couple to standard model currents. The flow of electric charge we're familiar with.
So they don't feel our electricity.
It's not too much, yeah. If they interact with our world at all, it's through more complicated, higher order ways. Think of it like a very indirect whisper.
An indirect whisper.
Yeah.
Okay, so how could we possibly hear that whisper?
That's where this kinetic mixing comes in again. It's a bit like two nearby pendulums influencing each other's swing, but with quantum fields.
Oh.
For massless dark photons, there's a specific scenario where this mixing means the dark photon talks mainly to its own dark stuff. But our regular photon might pick up a tiny, tiny millicharge interaction with the dark sector.
So the regular photon gets slightly contaminated, letting it feel the dark side a little.
That's a good way to put it, yeah. Now, about those more complex interactions, the higher order operators.
Right, you mentioned those.
Theories suggest these interactions between massless dark photons and our particles happen through what are called dimension 5 operators. It involves the dark photon's field strength and things called magnetic and electric dipole moments.
Dipole moments, like tiny magnets.
Sort of, yeah. It describes the particle's intrinsic magnetic and electric properties at a quantum level.
Okay. So experiments are trying to spot the effects of these tiny dipole interactions. What have they found? Or what have they ruled out?
Well, because the interactions are expected to be so incredibly weak, the searches often frame the results using an effective energy scale called lambda, and the strength of that magnetic dipole bit, dm.
Lambda and dm, okay.
And interestingly, some of the absolute strongest limits don't come from labs, but from looking at the universe itself.
The whole universe is a detector. How does that work?
It's amazing, really. Astrophysics and cosmology give us these incredibly tight constraints. It's actually quite similar to how we search for other hypothetical particles, like axions, because the interactions often depend on spin in similar ways.
Okay, give me an example.
Right, so take star cooling.
Yeah.
Things like red giants, white dwarfs, they're like incredibly sensitive thermometers.
Uh-huh.
If massless dark photons could be produced inside them, maybe by electrons wiggling around in that dense matter.
They'd carry energy away.
Exactly. The star would cool down faster than our standard theories predict.
And we don't see that.
We don't. The review has the equations linking this potential energy loss to a coupling strength, REA, and the dark photon stuff. Since the stars cool like we expect, we get really strict limits on how strong that interaction can be. White dwarfs and red giants give the tightest bounds on this RA.
So, normal star behavior puts the squeeze on dark photons. Cool. What else?
Supernova 1987A, that exploding star nearby.
Ah, I remember that.
It was a goldmine for particle physics. If too much energy had escaped the collapsing core via dark photons emitted by, say, protons and neutrons.
We'd have seen something different, like maybe fewer neutrinos.
Possibly, or different timing. The point is, what we did see was consistent with standard models, meaning not much energy could have escaped via dark photons. Again, the review links this to another coupling, a coan, giving us another strong limit.
Wow. Using exploding stars light years away. It's mind-boggling. What about the really early universe? Big Bang stuff.
Yep, Big Bang nucleosynthesis, BBN when the first light elements formed, and the cosmic microwave background, the CMB, that afterglow, they're sensitive too.
Oh.
If dark photons were around and interacting then, they could have messed with the balance, changed the amount of helium or deuterium we see today, or slightly distorted the CMB.
And they didn't.
Doesn't look like it. For everything to line up with observations, any dark photons must have sort of stopped talking to normal matter very, very early on, decoupled. This sets conditions on their average interaction strength, those dipole properties, and that energy scale.
So the universe's baby pictures also constrain them. Okay, let's come back to Earth. Lab experiments, colliders.
Right. We do look here, too. Some experiments hunt for incredibly tiny new forces between particles that depend on their spin.
Exotic spin forces.
Yeah, mediated potentially by exchanging these massless dark photons. The review mentions a formula for this potential force tied to the dipole moments and super delicate experiments using helium atoms, ions trapped in fields. They've put limits here.
Incredible precision. What about particle properties, like the electron's magnetism?
Good question. The anomalous magnetic moment. Massless dark photons don't contribute directly much. It's a higher order effect. But we measure the electron's magnetic moment with absolutely insane precision. That tiny uncertainty still allows us to constrain the dark photon parameters. There's an inequality in the review showing the allowed range.
So even if it's indirect, precision matters.
Hugely. The muon's magnetic moment, muon, gives another limit, but it's weaker because our measurement isn't quite as sharp as for the electron.
Got it. Any other lab constraints?
Yes, a big one comes from kaon decays. There's a particle called a positive kaon, K plus A. An experiment, E949, looked very carefully for it decaying into another particle, a pion, plus Tion, plus an invisible dark photon, A.
K plus E plus A.
Exactly. They didn't see it happen nearly as often as some theories might predict, which gives another strong limit on that dark dipole scale we talked about.
And the big colliders, LHC, LEP before it.
They look too. A key search is for particle collisions, say electron-positron, that produce just one ordinary photon plus. Nothing. Missing energy.
The nothing being the invisible dark photon carrying energy away.
Precisely. That's the signature. Monophoton plus missing energy. They've done these searches at LEP and the LHC. Important work. But so far, the limits from these collider searches for massless dark photons are generally not as strong as the astrophysical ones.
So the cosmos is still winning for massless searches. Given how tight all these limits seem, especially from astrophysics, is there any realistic hope of actually seeing a massless dark photon?
That is the multi-billion-dollar question, isn't it? It's definitely very, very challenging. The constraints are severe.
But not impossible.
Not impossible. The review suggests a few avenues. Maybe interactions involving heavier standard model particles are less constrained by stars. Or maybe we need to look at flavor off-diagonal stuff.
What does that mean?
Where the dark photon interaction changes the type of particle, like turning a muon into an electron, metaphorically speaking. Those kinds of interactions aren't typically constrained by the stellar cooling arguments.
Okay. Different interaction types.
Exactly. Or maybe just going to extremely high energies at future colliders could make these subtle effects pop out more. The review even notes that a relatively large dipole effect might still be hiding if the fundamental scale sectal is very high, like 1 TeV, perhaps accessible at future lepton colliders.
So look harder, look differently, look at higher energies. Got it. Now, you mentioned milli-charged particles earlier. How do they fit in?
Right. That's a related idea. What if particles in the dark sector aren't totally dark, but have a tiny fraction of a normal electric charge? A millicharge.
So they'd interact directly with our photons, just very weakly.
Exactly. And just like the massless dark photon-mediated forces, these millicharged particles are also heavily constrained. Limits come from everywhere. Star cooling again, RGs, WDs, SN 1987A, cosmology, NEF, positronium decay, dedicated searches at SLAC, neutrino experiments, LEP, LHC, CMB data, the list goes on.
So any tiny electric connection to the dark sector is also really restricted.
Okay.
To make sense of all this, a review mentions a minimal model of the dark sector.
Yeah, moving into more specific theory now, this minimal model tries to provide a more concrete picture. It introduces dark fermions, think dark electrons or dark quarks,
Okay.
and importantly, it introduces scalar messengers. These are new particles that act like bridges. They can interact with both standard model particles and the new dark fermions.
Messengers, connecting the two worlds.
Precisely. The review lays out the math, a specific type of interaction. It even splits the dark fermions into types Q that interact like quarks and Chi that interact like leptons via different messengers S and Phi.
Okay, so dark quarks, dark leptons, messenger particles.
Yeah.
How does this framework help interpret the experimental limits?
It allows us to connect those abstract limits like the dipole moments or the scalar back to more fundamental things, the masses of these new dark fermions, MQ, M, masses of the messengers, MS, MC, and how strongly they all interact, couplings, IL, IR, mixing parameters.
So it translates the experimental constraints into limits on the actual properties of these hypothetical particles.
Exactly. Instead of just saying, oh, must be large, we can say this combination of messenger masses and couplings must be constrained.
Right. And what do the translations tell us?
Well, cosmology suggests the dark fermions probably need to be reasonably heavy, like above 1 GeV, or interact very weakly to avoid messing with the CMB.
And the messengers, these bridge particles.
Since they interact with our stuff, we can look for them at colliders. They resemble hypothetical supersymmetric particles like squarks and leptons. Searches for those at the LHC can be reinterpreted to mean the quark interacting messengers, S, should be heavier than maybe 940 GeV, and the lepton interacting ones heavier than maybe 290 GeV.
So pretty hefty, if they exist. How do the star cooling and electron magnetic moment limits look in this model?
They translate into quite complex constraints involving the messenger masses, dark fermion masses, couplings, and mixing parameters. The review shows the specific equations. It becomes a relationship between multiple unknowns.
Does this model offer any loopholes? Any way dark photons could still be hiding more easily?
It offers flexibility. For instance, the review notes that even with the constraint from the muon's magnetic moment, you could potentially still have new physics effects show up at a scale like 1 TeV if the dark fermion masses are small enough. It's not a simple one-to-one scaling anymore.
Interesting. So what's next for massless dark photon searches? Any exciting future experiments?
Definitely. There's a growing interest. Flavor physics looks promising, studying rare decays of particles like kaons, Na62, Hyperion, or charmed particles at Big Ben.
Because those flavor-changing interactions aren't hit by the star limits.
Exactly. Also, high-energy colliders will keep looking for that monophoton plus missing energy signature with more data and higher energies. There are more exotic ideas, too, like using collective electron spin waves, magnons in materials, the QUAX proposal.
Yeah.
Even looking for subtle effects on gravitational waves from merging neutron stars.
Wow, using gravitational waves. That's creative. Okay, so the hunt for massless dark photons continues. Let's switch to the other type, the massive dark photon. What's the big difference there?
The crucial difference. A massive dark photon can couple directly to the standard model electromagnetic current.
The flow of regular charge.
Yes. Its strength is set by this mixing parameter, epsilon. So it has a direct, albeit possibly very weak, connection. The key parameters we hunt for are its mass, Ma, and this mixing strength.
Okay, direct coupling. How do we make these in experiments, and how do we see them?
Production can happen in several ways. Bremsstrahlung, where particles radiate them off, particle-antiparticle annihilation, decays of heavier particles like mesons, or in high-energy collisions via the Drell-Yan process. Figure 3.1 in the review illustrates these nicely.
And seeing them.
Depends on the mass and what they decay into. If the mass Ma is above roughly 1 MeV, twice the electron mass, it can decay into visible standard model pairs, electron-positron, muon into muon,
Right.
or even into hadrons, particles made of quarks, if it's heavy enough. The equations are in the review. An interesting point. The decay rate depends on epsilon, but the relative probability of decaying into electrons versus muons versus hadrons, the branching ratios, doesn't.
So we look for pairs of familiar particles popping up.
That's one main strategy, yes. Looking for visible final states. We might see a bump in the combined energy or invariant mass of the pair, indicating a new particle decaying.
Or resonance.
Exactly. Especially if epsilon is small, the dark photon might live long enough to travel a bit before decaying, creating a displaced vertex away from the main interaction point.
Okay, visible decays. What's the other way?
Looking for the invisible, if the dark photon is produced but then decays into dark sector particles that our detectors don't see.
Ah, back to the hidden sector.
Right. We'd see missing momentum or missing energy in the event. This happens if the dark photon mass is more than twice the mass of some dark sector particle. That can.
R2 message.
Yes, and if the dark sector interaction strength, ECA D, is much stronger than the mixing interaction, these invisible decays might even be the dominant way it disappears.
That's important. Many visible searches assume no invisible decays are possible.
Correct. It's a key assumption. Now, what if the dark photon is really light, less than 1 MeV?
It can't decay into electron-positron pairs then.
Right. It doesn't have enough mass. So for these very light ones, we need different methods. Looking for subtle energy loss effects in stars or the sun, or maybe direct detection signals in dark matter experiments.
Okay, different mass ranges, different strategies. Let's talk limits. For MA1 MeV decaying visibly, where have we looked?
A lot of places. Collider experiments like NA482, A1 at MAMI, LHCb, CMS, BayBar, KLOE, they've all searched for those bumps, those resonances in dilepton pairs.
Electrons are muons.
Yes. These are generally sensitive to larger mixing values, say epsilon bigger than 10 Yau and masses up to tens of JeV. Then there are beam dump experiments.
Firing beams into targets.
Yeah. E141, E137, E774 CHARM. They produce dark photons via bremsstrahlung or meson decays in the dump, then look for decays downstream. These are often sensitive to smaller epsilon, maybe 10 other to 10 year, and typically lower masses below a few JeV. Figure 3.3 in the review shows all these limits beautifully.
So big chunks of that mass epsilon plane are already ruled out for visible decays.
That's right. Plus, there are constraints from SN 1987A energy loss again, and that precise electron magnetic moment measurement provides an indirect limit too.
Okay, what about the invisible decays? Still for MAL1 MeV.
Here, you're looking for missing energy or momentum. The best limits currently come from the BayBar experiment at SLAC and the NA64 experiment using electrons at CERN.
And 64E.
Yes. Their results looking for missing energy have pushed beyond older limits from KN decays. Figure 3.5 shows how these invisible search limits complement the visible ones.
Covering different parts of the map. Okay, now the really light ones. Mass below 1 MeV. Where do the constraints come from there?
It's a real mix, precision atomic physics looking for tiny shifts in energy levels in atoms, like the Lamb shift or forces between particles. Nuclear experiments like Texono, experiments originally built for axions, helioscopes like CAST, light shining through walls like LSW, even dark matter detectors like Xeon 10 have been adapted to search for these light dark photons too.
Repurposing experiments.
Yeah.
Smart.
Very. And astrophysics hits hard here too. How stars on the horizontal branch or red giants evolve, even processes in our sun. They're very sensitive to energy being transported out by light dark photons mixing with ordinary photons in the stellar plasma. These give severe constraints.
Plasma effects. Interesting.
And cosmology, the Kobe-Firis measurement of the CMB's black-body spectrum, is so precise, it limits the possibility of CMB photons oscillating into dark photons on their way to us.
Wow. Okay, that's a lot. You also mentioned, what if the dark photon is dark matter?
Right. If this massive dark photon itself constitutes the universe's dark matter, then a whole other set of incredibly strong constraints kick in.
It's stronger.
Oh, yes. Observations of dwarf galaxies, the temperature of intergalactic gas clouds near our galactic center, potential distortions in the CMB spectrum from decays or annihilations, energy injection in the early dark ages, effects on BBN and the number of neutrino species, diffuse X-ray backgrounds, all these limit the possibility.
So basically, if it's dark matter, it can't interact or decay in ways that would mess up what we already observe.
Exactly. And on top of that, all the direct detection dark matter experiments, Xenon 1T, DAMX, Super CDMS, Sensei, LUX, Pandex, you name it, they are directly sensitive to dark photons in this mass range, potentially scattering off their detector material. Figures 3.7 and 3.8 in the review put all these astrophysical and direct detection limits together. It's a very constrained scenario. Even axion helioscopes can set limits.
It really sounds like if the dark photon is dark matter, it's hiding extremely well. What about the future for massive dark photons above 1 MeV? New experiments coming.
Oh, absolutely. It's a very active area. For the 1 MeV range, looking for visible or displaced decays, we've got Bell II, the LHCb upgrade, Na62 in dump mode, Na64E plus air, awake, phaser, Sequest, HPS, MESA, lots of acronyms.
Yes. Covering different mass and coupling ranges.
Exactly. Figure 3.4 shows the projected reach of many of these. They aim to push into unexplored territory. And for higher masses, the high luminosity LHC and maybe future colliders like the FCC could extend the search significantly.
And for the invisible decays.
Specific experiments are targeting those too. Upgrades to Na64E plus Bell II, again, proposed experiments like Claver, PADME, and especially LDMX at SLAC are designed precisely to look for missing energy signals characteristic of invisible dark photon decays. Figure 3.6 shows their potential.
And efforts continue for the 1 MeV range too.
Yes, although maybe not captured in a single figure like the others, there are ongoing and planned efforts pushing sensitivity in that lower mass region as well.
Great. One last parameter set you mentioned.
Huh.
Y and EMG for invisible decays to dark matter.
Right. Yang is a combination of parameters, including epsilon and the dark sector coupling, that's often used to quantify the signal strength when a dark photon decays invisibly to dark matter particles of mass m.
Okay.
Figure 3.9 shows the current limits on Y versus the dark matter mass m from experiments like Baybar, Na64E, beam dumps like E137, neutrino experiments like LSND and Mini Boon, and even direct detection like CREST and Exino.
And the future there.
Big potential improvements expected from future experiments like SHIP, BDX, beam dump facilities at Fermilab like SBND, LDMX again, and next-generation low-threshold direct detection experiments like SenseI and Super CDMS. Figure 3 shows these exciting prospects.
So across the board, for both visible and invisible, massive and massless, the search is really ramping up.
It really is. So let's try and pull this together. This deep dive has shown us this really fascinating theoretical idea of dark photons and just a huge diverse range of experiments trying to find them.
Yeah.
For the massless ones, the astrophysical limits are incredibly tough. It means if they exist, we're likely only going to see them in very specific ways, maybe high energies, maybe rare flavor-changing interactions. Very challenging.
Right. And the massive ones.
We've definitely carved out large regions of the parameter space, ruling out many possibilities, but as the review highlights, there are still these really interesting gaps, these windows that remain open.
Where are they, roughly?
One key window is for visible decays, for masses maybe above 100 MeV or so, and mixing strengths epsilon somewhere between, say, 10 O and 10 onorn. That region is tricky for current experiments.
Okay.
And the other big one is that very low mass region, especially the possibility that a very light, massive dark photon could actually be the dark matter. That remains wide open and intensely interesting.
So despite all the searches, no definitive signal yet, but clear targets remain.
Absolutely. And the next generation of experiments we talked about, they are specifically designed to probe these remaining windows with much better sensitivity. It really feels like we're pushing into potentially discovery territory.
It's a fundamental quest, isn't it? Trying to figure out if there's this whole other layer to reality interacting with us in subtle ways.
Exactly. New forces, new particles, understanding dark matter. It's fundamental.
It really leaves you thinking, what is the nature of this dark sector? Is dark matter tied up with dark forces, with dark photons? Could there be something completely unexpected waiting there? What would it actually mean if we found this dark light?
Profound questions. And hopefully you, the listener, are inspired to think about them too. If you want to go deeper, that review paper, 2005.01515V3, is the place to start. It really lays out the landscape.
A landscape where the exploration is definitely ongoing.
Absolutely. The search continues.